Algorithms seem complex, but they are just a way to solve a puzzle. But they are often explained in a language we don't understand. So first, let's put this language in a way that we do understand, and then we can really grasp the difference in these algorithms. Let's continue our series on algorithms with the second part of uninformed search algorithms. In video 1, we looked at the 5 algorithms and why would you use them with examples, and here we start looking at these algorithms with a technical overview. We can think of the algorithms as how they visit each node in a tree or a graph. Are they complete? Well, if you're trying to find a node or the value in a node, and the algorithm does find it, it's said to be complete. So assuming there is a solution, and your algorithm finds it, always finds it, then it's complete. What about optimal? Well, again, we're trying to find a node or the value in a node. If your algorithm finds the least cost path, then it's optimal. So the shortest path, does it get to the node in the optimal way? Time complexity. Now, time complexity is not measured in time. So if you're looking at algorithms, you can't use time as a measurement. What you can do is use the number of operations. So in these search algorithms, these would be the amount of nodes that are visited. So for example, here we've got breadth first search and we want to get to node 5. We would go 1, 2, 3 and then 4 and 5. So we visited 5 nodes for a breadth first search. Alternatively, with the depth first search, we would go 1, 2, 4 and then 5, which is visiting 4 nodes. So you can see we don't look at time, we just look at the nodes that it's visited. Now, space complexity. Is this to do with space? Well, sort of. Space in the sense that it's to do with memory. So if you look of order of magnitude with these order of 1, order of n squared, etc., this is what we're talking about with space complexity. Now, other terms, we look at branching factor. So this is really how many children wide it is, if you like, the breadth. So branching factor, here we've got a tree that's got 2 children on each node, so the branching factor is quite simple, it's 2. The other obvious metric would be depth. So we've already seen the root node is at level 0, we've got level 1 and level 2, so that would be depth of 2. Now, depth can be unlimited, can be infinite. So sometimes you might see M for maximum depth of the state space, which is a term used for the tree or the graph. So here we've got breadth first search. Now, in memory, we put the root node 1, and then the children 2 and 3, and then the children of 2 and the children of 3. So breadth first search keeps all the nodes in memory, which is important. So what we're looking at, each level, we're going to put all of the nodes in. So if you like, how many children there are, as the breadth would be B, and the depth, for example, we had depth of 2. We've also got the root node so that we add 1 to D depth. So for example, here, if we've got 0, 1, 2, which is like 3 levels, and there are 2 children each time, that's 2 to the power of 3, so maximum of 8 units in memory. You can see here the tree has actually got 7 nodes, so you can also think of 2 to the power of 3 is 8, so 7 is less than 8, so the maximum is going to be like 1 less than breadth times by the D, the depth. Now, depth first search is completely different, and the reason why is that it pops out nodes from memory. Yeah, it uses a stack. So what it really does is it only keeps the path in memory to look down the tree, the path to the node that it's searching for. So this is different because it uses less space in memory. So let's summarize that. So breadth first search, we've already seen it's finds the shortest path, doesn't explore really long ones, doesn't go on massive detours around graphs, etc. So it's quite efficient at finding like shallow problems, if you like, ones that are close to the root node. So used in different aspects of AI. So it is complete and it is optimal. Now remember, we looked at time complexity, which isn't time. So let's have a look at the number of operations used, or nodes visited if you like. Space, remember this is in memory. Well, breadth first search keeps every node in memory, so it's memory intensive. Breadth first search is quite simple, but it's not very efficient, especially memory wise. So only really used for shallow problems and complex in natural language processing. Now let's compare breadth first search and depth first search. So depth first search, quite simple, memory efficient, and this does the opposite. It does go looking for long paths, if you like, and not really for shallow problems. So very different from breadth first search. It's not complete. It falls into problems, if you like, where you have like a path in a tree or a graph that is very long but doesn't have the solution. And depth first search can be quite inefficient. Now it can be made complete if it's slightly modified. So if you tell the algorithm not to repeat paths, for example, and your problem is finite, the tree or the graph isn't infinite in either width or depth, then it is complete when it's modified to be so. Not really optimal. We can see the time and space complexity. Here you can see where the maximum depth is quite deep and the solution is quite shallow, then you can see how depth first search is inefficient. Whereas if the tree is very wide and dense and has a high amount of nodes in the breadth, then it will be better, more efficient than breadth first search. So we only keep the nodes that we need to work out the path in depth first search. So the memory is actually of linear complexity. So the depth first search, memory efficient, explores very deep but does get stuck if that's not what you want, and it doesn't always necessarily find the shortest path. Now you may see complexity written in different ways, so we can use, for example, the nodes are called vertices with edges connecting them, or we could even use just width and depth rather than breadth and depth. So you'll see the breadth first search as the order of vertices plus edges, and then it depends on if you use certain techniques. So we can see slightly different notations when we look at complexity. Here we've got the same, except for breadth we've got width. We've seen a very good and clear example in the past. Now we haven't got access to that, but we've got a quite similar example. So we've used AI to make the calculations, but the point is that we're using statistics to show the difference between breadth first search and depth first search. So we've got a tree that's 10 nodes wide, we've got memory usage and the speed of a computer, 1 million nodes per second processing, no big long depth problems, and we're going to look at trees that are 5, 10 and 15 in depth. So first of all, look at the statistics for the breadth first search and depth first search, which aren't important, but when we compare them, we can see the time complexity is the same. The estimations for the 3 different size trees are the same. That's what the main point of this is. You can see obviously once it's a tree or a graph is deeper, then it's going to take a huge increase in time to achieve that. Now the main difference between the two algorithms is memory. With the breadth first search, it keeps all the nodes in memory, which is a hugely inefficient approach if memory is going to be a problem. And it is going to be a problem when you look at these numbers. So if memory is an issue, you would certainly not use breadth first search. The other algorithms, we've got depth limited search, iterative deepening search, uniform cost search. Well, depth limited search is pretty much the same as we know depth first search, except for there's a limit. So we really have the same efficiencies except using the limit rather than the maximum. So you'll see the exact same details as a depth first search, except we change the maximum to the limit when we're looking at the statistics. Again, linear complexity on space. Iterative deepening search, which kind of merges the two approaches essentially. So it uses the depth first search with a limit. So again, we have similar statistics to the depth first search with the iterative deepening search, obviously with the limit when we're looking at the depth. Uniform cost search is a bit different. It's actually more like an informed search in some ways because we have costs. But the other algorithms all assume there's a cost of 1. So if there's a cost of 1, uniform cost search is not needed. But if there is a different cost than a cost per step of 1, then we use uniform cost search. So it's not really comparable with the other algorithms. Is complete, is optimal, but its efficiency, its complexity, both time and space, is based on the cost and the maximum cost. So in summary, here we have our 4 algorithms. We don't really compare uniform cost search. We have, are they complete? Are they optimal? What's the time? And what's the space complexity? Okay, I hope you enjoyed that. Next part of this series, we're going to look at informed search algorithms.